Good evening, everyone. Welcome to the Institute Colloquium. It's a real pleasure to have Krishnendu Sengupta visiting us from IACS. Krishnendu got his undergrad degree at IIT Kanpur and then went on to do a PhD at the University of Maryland College Park, working with Viktor Yakovenko. Then after a couple of postdoctoral stints, one at Yale with Subi Sachdev and Steve Gerwin, and at University of Toronto with Yongbai Kim, he returned to India, first as a faculty member at the Harishchandra Research Institute in Allahabad, then at SINP, and then he's moved to IACS, where he's been ever since. Krishnendu is very well known for his contributions to understanding correlated systems in solid-state settings as well as in ultracold atoms, something we'll hear about today. And he has won many awards and prizes for this. In particular, he's a member of all three Science Academies of India. He's a winner of the Bhatnagar Prize. And very recently, he's been awarded the J.C. Bose Fellowship of the Science and Engineering Research Board. Okay, so without much further ado, Krishnendu, the stage is all yours.
Okay. So first of all, I would like to thank the organizers, particularly Shayantan, for this invitation. It's a real pleasure to be here after quite a few years. And I would also like to thank Ajit for this really kind introduction, much of which is quite exaggeration, but okay. The topic of the talk today would be a rather pedagogical introduction to how we emulate strong correlation using ultracold atoms as a platform. And I have been working on this for quite some time, and so let me just first try to acknowledge all my collaborators out here, and I'm sure I have missed a few names, but particularly to my postdoc mentors Steve Gerwin and Subi Sachdev, with whom I started working on this subject, Nicola, who had been a mentor, and I would also like to acknowledge all my students, and particularly Bhaskar and Madhumita, with whom some of the recent works have been done, and Arnav Sen, who is a next door colleague and with whom I really talk a lot about these systems. So here is a brief outline of the talk. So first I'm going to talk a bit about this system of ultracold atoms and just give you an idea about how we emulate strong correlations there using just atoms and light, and in particular how it sort of leads to the Bose-Hubbard model, which is the paradigmatic model in the field when it comes to bosonic atoms. And then I'm going to go into several other topics, the tilted lattice, the Reedburg chains, and the Reedburg ladder, if I have time. Each of these emulates some strongly correlated model, which has its own phase transitions and other things. And I'm going to kind of tell you how theory and experiments run hand in hand in explaining these features. Okay, so, and at any point, if any of you have any questions, please stop me and ask. Okay, so a very naive introduction to these ultracold atoms. So when we say cold, what do we mean? I mean, it starts from freezing point of water probably, or maybe even 300 Kelvin when most people in Calcutta bring out their sweaters. But in a laboratory, it goes all the way down to say liquid helium and even lower temperatures than that. But in a typical condensed matter laboratory, that's pretty much it. Whereas in these ultracold atoms, you can use techniques involving laser cooling and something called evaporative cooling, which I'm going to briefly explain, and go to temperatures which are orders nanokelvins. Okay, and now I think even tens or hundreds of picokelvins are achieved, and this really makes these systems the coldest place in the universe, the coldest known place. Okay, remember outer space is like 2 Kelvin or so. Right, and the question that comes in immediately is that how do you measure such temperature? It's not like you can just stick in a thermometer and get a reading out of this. So, and that technique by itself is a really interesting thing. For cold bosons, what you do is that any set of atoms you take and you really cool it to this temperature, and typically the prototypical atoms that are used are 87 rubidium atoms for various purposes, but if you take a bunch of those atoms and you cool it to this temperature, then what happens is that the momentum distribution of these bosons, because it's in a BEC state, is all centered around k equal to 0. Okay, this a peak like this. Now, the colder it is, the sharper the peak, and the width of this peak gives you a measure of this temperature of the system, and it's really by measuring this width of this peak you can find out how cold your atom is. So how do you do this cooling? I mean, there are several stages of it, and two of this is something that I am going to explain. So the first one is called a Doppler cooling of atoms. So you cool these atoms by conventional techniques and get them to about a millikelvin or so, and then what you do is that you place them in a trap and put lasers from all different directions, okay, so circularly polarized lights. Now what happens here is that you tune the laser frequency to just below the resonant frequency of these atoms, so that when the atoms are moving towards this photon in the laser, you know, it gets a higher probability of getting scattered or absorbing that photon. That's because of Doppler effect. If you are sitting on the atom, you are going to see that the frequency of light is just right for inducing a transition to higher level. So this means that because the atom is traveling towards the photon, it's going to impart some momentum to the photon when the collision occurs, and therefore lose some momentum. But this is not the entire story, because the atom gets excited to a higher state because of absorption of energy from the photon, and then after some time it just comes back to the lower state, emitting another photon. Now this photon is random because it's spontaneous emission. It can be, so for example, if I take a one-dimensional system, it can be emitted either along plus x or minus x. If it gets emitted along plus x, then the atom essentially loses some momentum, and therefore it slows down as a combined effect of these two processes. And therefore, statistically speaking, because it's a random process, over time the atoms lose their momentum, and therefore it gets colder. Okay, and this leads to creation of what is called optical molasses, and this can go up to a microkelvin temperature. By the way, I should remark that, you know, this looks like a very simple process, but the theory of this is something which was properly developed only during 90s. In the 70s, people understood this Doppler cooling, and they predicted a temperature bound for this Doppler cooling. And when people actually did experiments, they found that they could go to a much lower temperature, and this was a puzzle throughout the 80s, which got explained with some remarkable work in the 90s by Bill Phillips and others. Then what happens is that after you are done with this optical molasses and you have achieved this microkelvin temperature, what you do is an evaporative cooling, where you take these atoms. This thing is really not working probably. Why is it? Okay. So and then you put them in a magnetic trap, and then what you do is that you slowly lower the top of this trap. Now the distribution of the atoms in this trap is also their energy distribution. The higher energy atoms are towards the top of the trap, because trap is like a potential. And when you lower this energy, what happens is that these atoms from the top just move away. This is the same mechanism by which your coffee gets cold in a winter day. Okay, this is why it's called evaporative cooling. And therefore, if you do it carefully enough, you get a lower volume of this condensate, but that condensate is way cooler than what you started with. And this leads to temperatures of the order of tens of nanokelvins, and people have now gone well below that. And this is well below critical temperature of any Bose-Einstein condensate for standard atoms, and therefore you get a BEC. Okay, so this is how these ultra cold temperatures are roughly generated. And now to have correlations, what people do is that they try to form a lattice to put these bosons in, but this lattice is formed by light. So what you do is that you apply counter propagating lasers so that you form a standing wave of light. Now any atom has a polarizability which is defined by this alpha, and therefore if the intensity of the light is given by mod E square, its electric field square, then the atom feels a potential which is minus alpha times something else. Okay, can you see what's wrong with the pointer? I can't seem to get battery input. So yeah, so the atoms feel a potential, which is this polarizability times the intensity of the laser. Now this polarizability is something which is a function of the applied frequency of the laser as well as the characteristic of the atom. And so if you tune it right, this alpha can be greater than 0, which means that the atom is going to go and sit at the bottom of this potential formed by light. Okay, and this is how you generate a lattice made out of light with the atom sitting in the boson in the bottom of this lattice, and this gives you block theory for bosons. Okay, because in solid state we always talk about fermions in a lattice, and then we talk about block physics of that, and this is how you generate for atoms. Now this is the experiment which started this field long time back in 2001, and this was done by Emanuel Bloch's group in Germany. So what they did is that they took these ultracold atoms and they put it in a trap, they cooled it so that they have a Bose-Einstein condensate. Then they put in a laser creating this standing wave of light, a lattice, and the intensity of this laser is ramped up to a time window of 20 milliseconds up to a value which is called Vmax or V naught out here. Then they allow the atoms to sit here for a certain time, for about 20 milliseconds or so, and then what they do is the measurement process. Now what do they measure? They essentially drop the trap as well as switch off the laser, this lattice due to the laser, and let the atoms just fly out. Okay, because it's a free flight to some very good approximation, the position of this atom during this free flight after a certain time depend on its initial velocity inside the system. Okay, because if it's a free flight, it just depends on this initial velocity, and therefore if you measure, let me just show you this, if you measure the position of these atoms on a screen after you have switched off this laser after some time, then what you get essentially is the momentum or the velocity distribution of the bosons inside the trap. So the position distribution of the atom on the screen gives you the momentum distribution of the boson inside the trap, and it's all because that to a good approximation this is a free flight of bosons. Okay, so we see this, that when this lattice is essentially very small or close to 0, you see that all the bosons are in the center of that screen, which means that it is at k equal to 0 momentum. And as you increase this thing, you see these side peaks developing, and that's because of the periodicity of the lattice. But around this, let's say around 14 times some recoil energy, which is the natural energy scale with which you measure your energy, and this is the energy scale that you create out of the mass of the boson and the wavelength of the laser light. That's the natural energy unit of the problem. So when this potential becomes roughly around 14 times a year, you see that this central peak gets destabilized, and beyond that it's all a spread of blob. Okay, this means that the bosons are almost everywhere on the screen, which means its state inside the trap contains all possible momentum, which essentially means that it's very well localized, simply from Heisenberg principle. Because if it's a combination of all momentum, then its localization is so it's very spread out in momentum space, and therefore it must be very well localized in real space. So here is a cute picture about how you measure this stuff, and also from there they can reconstruct this in a more beautiful way, which is something like this. And here you see that at low lattice strength you have this central peaks, which is telling you about having superfluidity, and here you just have a central blob which tells you that you are in a localized state. Okay. So by increasing the strength of this lattice, you can simply localize this boson and change them from a BEC, which is a completely delocalized state of boson, to a localized state. Okay, which as we will see is a Mott insulator. So to explain this theoretically, one comes up with a model, and this model is very simple. It was given by many people at different times, and Professor Ramkrishnan is one of them. The first paper, I guess, was written by Matthew Fisher and others, and then there are many other people who worked on this. But the logic behind this is very simple. You see that when you put in a laser, it gives a lattice for this atom. So to describe the motion of these atoms, you just take a tight binding hopping model, which is standard, and this it just tells you that the atoms, the kinetic energy of the atoms in the presence of this lattice means that it can move from one given site to the next, and this hopping amplitude just depends on the overlap of the wave function of the atoms between these two states, okay, two lattice sites. And then these atoms are neutral, they don't see a Coulomb interaction, but nevertheless they have some interaction potential like van der Waals. But this is approximated by just an on-site interaction stating that these atoms are going to see each other with a repulsive interaction only if they are on the same site. Okay, and this is the second term which essentially takes care of that. And then we put in a chemical potential and just try to see what phase diagram we get out of this. Okay. So here are some typical energy scales in the problem, that the energy levels of these atoms in a single level is roughly delta En, which is 5 times the recoil energy, and that's larger than U. So we are happily sitting in the lowest band. We don't really need to consider other bands in this problem. And U can be tuned to 10 to 300 times the hopping. Okay, if you want to go deep inside the Mott phase. And in the superfluid phase, of course, you can be, T can be put to 0, so you don't need to worry about this. So here is so what we see here is a transition from a localized state to a superfluid state, and the theoretical prediction is that this is a Mott superfluid, Mott insulated to a superfluid transition. So let's just examine how that transition takes place. So one way to understand is the limit where this lattice is so deep that the hopping is close to 0. In that case, the Mott state depends on the relative magnitude of this U, the interaction, and this chemical potential. And for, this should be mu. So for your chemical potential between 0 and U, it turns out that the Mott state has 1 boson per site. Okay, that's the minimum energy state. And this you can check by simply putting in numbers in this on-site Hamiltonian, and it's not so difficult to see. But then we can ask ourselves the question, what happens if we add an extra boson on top of this Mott state? What happens is that once you put in this boson, it costs an energy U minus mu because you have put in an extra particle and therefore you gain a chemical potential, and U because on this side the boson now sees the other bosons and they have an interaction cost. But now you see, it's easy to see that it really doesn't matter if you put this boson on the site here or there, and once you put on a boson here, it can simply hop from one site to another with no extra energy cost. And this leads to an energy gain of 2 times T times the number of nearest neighbors, because the atom can go in all the nearest neighboring direction. And this tells you that this excitation energy touches 0, which means destabilization of the original ground state, when there is a critical hopping strength, which is U minus mu by 2z. You could do the same thing by removing a particle, and that gives you a critical hopping strength of mu by z. And when essentially these two, so as you increase your hopping, either you hit this number, which is mu by z, or that one, whichever comes first gives you the destabilization of the Mott phase. And if you increase, and this leads to an onset of superfluidity. If you increase T further, you are going to get into a superfluid phase. And there are many ways to go beyond this simple picture. So people have done, higher order energy calculation that's due to Friedrichs-Monnian. There is this mean field theory, which was from Fisher in '89, and then TVR and others worked on this. And then there is of course quantum Monte Carlo, because this is a bosonic problem and it has no sign problem. So Nandini Trivedi and Kroth, they worked on this in the 90s. and there are many studies after that. But all of this predicts that this transition from a MOT to a superfluid phase is a quantum phase transition with a dynamical critical exponent z equal to 2, except when you are at the tip of the MOT lobe, where due to some extra symmetry it becomes z equal to 1. Whatever that dynamical critical exponent is, this is the only time I am going to refer to it, so don't bother if you are not familiar with this concept, but this is one of the exponents which characterizes a quantum critical point. So however, in any of this or all of these calculations, it's very hard to get nature about the information of the MOT phase, at least analytical understanding. So this is something that we worked on at some point. So what we did is to develop a strong coupling theory which gives you directly the Green's function of this system, both in the MOT phase and in the superfluid phase near this. And we could find out, so what this calculation gives you is a Green's function. This is called the whole branch, and this is called the particle branch. Sorry, this is called the particle branch, and this is called the whole branch of the Green's function, because you could have whole-like and particle-like excitation. And what this Green's function tells you that these have different these different spectral weights, both these branches, which is one property of this model, that it doesn't have particle symmetry. But but for the experimentalists, it's good to see that this gives you a momentum distribution which they can measure directly, which comes from trace of this Green's function. Okay, so that is something which was good about this model, that one could calculate this, and the answer simply turns out to be this spectral weight. Okay, so the momentum distribution is given by this spectral weight -1, but that's this thing. One thing that it predicts, and this is the spectral weight, and notice that this has the difference of the particle and the whole branch out here, and it turns out that when this goes to 0, which happens at the tip of the MOT lobe, for example, this essentially shows a peak. Okay, this z becomes large, and one can show that this nk would show a peak out here. And apparently this is called the precursor peak. So as you start from the MOT phase and you go to the superfluid state, if you measure the momentum distribution, you see that the approach to superfluidity is shown by a precursor peak which develops exactly at k equal to 0. And this is something that we looked at, and essentially there was a experiment by Ian Spillman's group in 2007 which had a reasonable match with our data. And so this precursor peak is something which is very well captured by this Green's function theory. So this is one way of understanding the properties of the MOT phase and in the strong correlation limit of these bosons. So now I am going to come to the another topic, which is this generating gauge fields with this light. And this is a slightly more complicated stuff. What one does is to sort of take these ultracold atoms, okay, and couple it to suitably designed linearly polarized Raman beams along plus and minus x. But now, instead of having the same frequency, they are shifted, the right and the left beam are shifted by a frequency delta L. So what it does is that it connects states, these three states of the Reedburg atoms corresponding to MF equal to 1, -1 and 0, with essentially with a shift in momentum. Okay, so essentially it turns out after some calculation, which I am not going to show, that these three states now get coupled to each other, and the coupling strength depends on this omega r, which is the amplitude of this external Raman lasers. But what it does is very interesting. What it does, if you calculate the dispersion of this bosons in the presence of these Raman lasers, the thing that you see is that this dispersion develops a minima not at k equal to 0, but at a shifted value which is given by something of the order of KL, which is some momentum scale. And if you measure this stuff, you see that with the increasing detuning, that is the difference of this delta omega L, which can be controlled by the difference of this right and left laser frequency, you find that this shift increases. Okay. It can be negative or positive, but it will keep on increasing. And this detuning of Raman coupling therefore leads to the shift of the dispersion of the atom. But what does that mean? This essentially means that you have put in a vector potential, because a shift in the dispersion essentially means what you were calling k before now becomes k minus k naught, which is exactly same as putting a constant vector potential in your problem, right? Because that's what it couples to. These experiments are unique in a way that they don't just create a gauge field, they actually create a vector potential in a given gauge. So in some sense, you know, this is not gauge freedom anymore. You have created a vector potential in a laboratory, and you can measure stuff which depends only on the potential and not so much on the field only. And in the presence of an optical lattice, and after doing some tricky things, you can make this dependent on the position, and essentially this gives rise to a hopping strength, which is this J, which precisely has this phase built in. Okay. So this is one way where by using an external Raman laser, you can generate an abelian gauge field. Okay. And you can actually see that it is really an gauge field. The reason is that you take this bosons, okay, and this cloud is essentially a picture of this bosons occupying real space. So what happens is that you image this cloud and you start putting in this delta, which was this detuning, which depends on this detuning, and you see that as you increase this, you have these dark spots, which is analogous to having vortices. Okay, and this is exactly the same type of spots that you would see when you take a condensate and you rotate it, where this, you know, the quote unquote magnetic field comes from the Coriolis force of rotation. Here, this gauge fields to it. So there is no gauge freedom. You have generated the vector potential, but nevertheless, if you have the right spatial dependence of this vector potential, you come up with a magnetic field, okay, which gives rise to effective magnetic field, which gives rise to vortices. The interesting part about this is that, look, these bosons are not charged, okay, so they shouldn't be seeing anything like electric and magnetic fields. But nevertheless, using light, you have created an effective magnetic field, which gives you a similar phenomenon as magnetic fields in a superconductor, for example, okay, namely vortices. Okay, I'm going to skip over this. You can also look into what happens in the Mott phase when you do this, but let me just skip into this. The only thing that I want to say about this is that in the presence of this vector potential, the superfluid insulator transition becomes very interesting, and it can give rise to unconventional quantum critical points, but that's something I'm not going to talk about. And also you can get some modulated superfluid stiffness, which has spatial distortion, so it's almost close to having a super solid out here. But let me now come to a different topic, which is tilted optical lattice. So I told you about generating artificial magnetic field out here, but let me now try to tell you how to generate artificial electric field for these bosons. Okay. And this is one way we do essentially create a strongly correlated system. So, okay, so for many years people have been thinking about breaking translational symmetry in this kind of system in the Mott phase, because it was theoretically understood that breaking these extra symmetries can give rise to very interesting physics. Okay, one way of doing this was to essentially put two species of bosons and engineer interaction between them, which can then give rise to different spin states or pseudo spin states, which are these two, the spin being the species index of the boson here. So the first species is called spin up, which is like a 1-0 state, and the second species is called a spin down, which is like a 0-1 state. And then by engineering proper interaction, you can get FM, AF, XY, etc. different phases in the Mott phase. But this is difficult to do because of experimental reasons. The other thing people was trying is to break this translational symmetry by putting in a nearest neighbor interaction, which is also very difficult to achieve for these bosons. But here, of course, nature of this quantum phase transition, etc., and having a competition between a broken U1 symmetry due to the superfluid versus a broken translational symmetry at certain fillings because of this VNI-NJ term. I mean, these things come into picture. But this again is experimentally very difficult. Experimentally, what is easy is to generate a tilt to this optical lattice. So I told you that by applying this counter-propagating laser, we created this optical lattice, okay, and the whole thing is sitting in a trap which traps the bosons. So the simplest way to generate this quote-unquote tilt is by shifting the center of the trap. Now, why is this like an electric field? The answer is that the trap gives you a harmonic oscillator-like potential. So if you shift its center, you get a shifted harmonic oscillator, which means it gives you a linear term for this neutral bosons, which is effectively like an electric field. Because if you think about it, a static electric field just gives you a linear potential term, right? So this is how one generates an electric field. Another way, which is experimentally more popular these days, to generate this tilt is to put in a magnetic field, but now a spatially varying linear magnetic field. And if you have a spin polarized boson, then the Zeeman term essentially gives rise to a linear term like this. And this also acts as an effective electric field for these bosons. Okay. So both any of this essentially at the end of the day gives rise to a term like this in your Hamiltonian, where this epsilon depends on the magnitude of this shift or the magnitude of the magnetic field that you put in, and this I is of course the space index, and this Ni is the density of the bosons. Okay, but notice that this particular term out here is exactly the same term that you would put in for a charged particle in the presence of a realistic electric field. And this is how you generate a quote-unquote electric field for neutral bosons. And there was an experiment, and I'm not going to get into the details of this because, okay, so this is the same experiment by the Greiner group, but here what happens is that in this point where this system was in the superfluid state, they put in a superfluid or Mott state, depending on what you have, they put in this tilt. That's their perturbation. Okay. So this perturbation leads to absorption of energy in the system, and therefore you see that this energy essentially leads to a split central peak, because now when you measure the momentum distribution, the atom is not in its ground state, it's not the ground state superfluid, but there is some excitation which has been produced. Okay. And they can measure the width of this peak to get an amount of energy that has been absorbed. And it turns out that in the Mott phase, that there is a sharp resonant absorption at fixed electric field amplitude, that is at the fixed perturbation amplitude, which is a signature of transition between definitive quantum states. Okay. So this is something that this tilted lattice does. So we have been, so one can try to think about why this is the case, what happens in the Mott phase. So to think about this, one thinks of this parent Mott phase, which has, let's say, 2 particles per site, okay, and now we have put in this tilt. Okay, so this is the Hamiltonian, and let us be in the limit where this tilt and the U, because I am deep inside the Mott phase, is large compared to both the hopping, which is W here, and mod U minus E, which is the difference between the electric field and the interaction energy. Now, once you think about this, you try to see what can destabilize this Mott phase and lead to energy absorption. Now, typically, if you put in an if you put in an extra particle or a hole out here, this is not going to happen. The reason is that now you can put in an extra particle out here. It's going to have some energy cost, but let's say you put that energy. But then the question is that can that energy cost be nullified by this particular particle hopping from one side to the other? And the answer is no, because now this particle essentially has a hopping term, but it also has an electric field term like this, because it sees the electric field. And this is the one-year star problem, which tells you that the eigenvectors are well localized and the particles don't move from side to side. Okay. So this is also in some sense the block problem, which tells you that things don't really go to infinity, it just oscillates within the first block band. So quasi-particles and quasi-holes do not lower their energy, and these are not the low energy effective excitation of this model, okay, in contrast to what you have seen for this other thing. So what we found is that what essentially are low energy excitations are this dipole kind of thing, where you take in one particle from here and put this here, because this costs an energy U minus E, and that when U and E are of the same magnitude can be very close to the ground state. So these are resonantly coupled to the parent mode state. And apparently then one can write in a Hamiltonian in terms of these dipoles. So these dipoles takes an energy U minus E to be created, and then because there is hopping, you see a particle can go from one side to the next, and therefore a dipole can be spontaneously formed, or it can go back, a dipole can be spontaneously destroyed. So this means that there would be a linear term like this. But on top of this, it turns out that there would be two constraints. One of them is that you can form only one dipole on a link, because the particle can hop only once. And the second thing is that, and this is something that I am not going to explain very well, but nevertheless it turns out that if you have a dipole on a given link between two sides, that is if a boson has hopped from one to another, you cannot have a dipole on the neighboring link, because that would mean that there would be an additional energy cost which is large. So the question is that suppose we have this, what is the phase diagram of this model? The phase diagram of this model essentially is easy to explain. So if your electric field is weak, so that U minus E is large, your ground state is the dipole vacuum, and the first excited state is single dipole states. Okay. However, if you are in the strong electric field limit, where your electric field is large, you see U minus E is a large negative quantity, which means that there would be maximum number of dipoles which would be formed. And this can be formed either on odd sides or on even sides, but not both, because you cannot form dipoles on neighboring links. And therefore, there is a Z2 symmetry with two degenerate ground state. The ground state will spontaneously break one of them, just like Ising model in a transverse field. And so the two limits are separated by a phase transition, because they have different symmetries. One breaks a discrete Z2 symmetry and the other doesn't. So they must be separated by a ground state, by a phase transition. And this is what we also found. So some exact diagonalization studies shows perfect scaling with all the right exponents that is required for the Ising model in a transverse field. And luckily, after almost 6 or 7, roughly around 7 or 8 years after we did this theory, there was some verification in experiments, again by Marcus Driner's group at Harvard. And okay, I can almost not see this, but anyway. So okay, so what happens is that in the experiment, what they do is that they prepare a 87 rubidium Bose-Einstein condensate with F equal to MF equal to 1, that is the spin of this stuff, and then they project a square optical lattice on it, okay, with this lambda, and ramp the lattice depth. So first I am going to tell you how they measure stuff, which is a bit different from this momentum distribution measurement. Now say after doing this, and you let the atom equilibrate, and then you have prepared a state. So how do they measure this? After the state is prepared, they suddenly increase the lattice depth to a really large value, so that the bosons effectively freeze for a large amount of time scale. Because if you ramp up the lattice to a very large value, what happens is that your hopping amplitude for the boson is exponentially down, and so the bosons are almost going to freeze. And then very ingeniously, what they do is to apply a light with the correct frequency and so on, so that the bosons can have light assisted collision between them on the same site of the lattice. So if there are two bosons on any side, they are going to interact with this light and just scatter with each other and leave the trap. However, if there are odd number of bosons, then there is at least one boson which is going to remain because it doesn't have a partner to scatter with. So this means that if you look into this, so you apply this light and let the even number of bosons move away from this lattice, and then you can image the remaining atoms. So this means that you are measuring parity of occupation of the state. You really do not know whether the whether the state had 2 atoms per site or 4 atoms per site, but you can distinguish between 2 atoms per site versus 3 atoms or 1 atom per site. So you can measure the parity of occupation. So it turns out that the probability of odd parity of occupation in a superfluid state, that is this number where this average n is the average superfluid average density of sites in a superfluid state, which is not a fixed number, by the way. In a superfluid, average n is not conserved, and this is just the average. N of course will have fluctuation, and so will this number, but this is just the average probably in some sense, and this is well below 0.5. While for the mod state, it depends. It can be either 0 or 1. Okay, because you can either have mod state with even occupation or odd occupation. This is. And so you see, as you move this thing in out from here, you see that these greens are signatures of measuring atoms. Okay, which means that you have odd number out here, and the black ones are the ones where you have even number, where it doesn't, where the light doesn't see any atoms. So this essentially means that this is sort of the mod state with odd occupation. Okay, and this is sort of the superfluid state. So this imaging gives you a clear distinction of site resolved measurement in between superfluid and mod state. But more importantly, it can detect parity of occupation, which would be interesting in this kind of this tilted lattice measurement. So in the next stuff, so let me just show you this and not bother you with details. So what they did is that they did this tilted atom, this tilted lattice measurement by applying a magnetic field, and they tried to find out the probability of odd occupation, and this goes from 1 to 0 across the transition. Okay. Now what this means is that you started with a state where there were 1 boson per site, that's a parent mod state, and you end up in a state where there are these dipole pairs out here. Okay. So you can go from here to there, and they could do it coherently, meaning that they can ramp up this tilt to get this transition, and then when they decrease the tilt, they again come back to this state. So it's a coherent quantum process which they checked in experiments, and this showed that some kind of odd even transition on the lattice is happening. In this. Of course, they don't know what kind of transition this is, because universality of this, exponents for these transitions are very hard to measure in experiments. But there is at least a difference of state that is going on, which is not inconsistent with the theory that was given before. Okay, so now let me come to the topic of experiments with Reedburg atoms. So this is another class of atoms which has become very popular in recent years for generating strong correlation, and the reason for this is so let me first explain the system. So essentially you again have these 87 rubidium atoms, but now you pump in with 2 different lasers with these frequencies, and essentially it generates a coupling between an excited state, which is R, which is a really high state of this 87 rubidium atom, and the ground state, which is this 5s of etc. This intermediate state has some 6p 3/2s type of stuff, and this just act as an intermediate state. The blue laser essentially couples the ground to this intermediate state, and the red laser couples the excited state with this intermediate state, so that the effective amplitude of transition between these 2 states depends on this omega, which is this omega b omega r divided by 2 delta, where this omega b and omega r are this frequencies of these 2 lasers. This small delta and the capital delta are essentially detunings, which tells you how much difference this applied laser frequencies have, compared to the atom levels. Okay. So essentially what it tells you is that this omega essentially couples you between these two states, Reedburg and ground. So in terms of a spin on each side, if this ground state corresponds to a spin down and the excited state corresponds to a spin up, then I have a sigma x term which has proportional to this omega. But there is also this thing that depending on this detuning delta, I have essentially it is energetically favorable or disfavorable for me to create an excited state. And here one can do this because there are these external lasers, so this term is still there. And then these are the two terms essentially which gives you the on-site terms which the atoms experience. However, the interesting thing here comes from the fact that once you are in a state, this excited state, imagine that you are in an excited state on a given site. The point is that if your next atom is also on an excited state, then there is a huge dipole interaction between these two. Okay, and this is the this is purely atomic physics property whose details I don't have good understanding about. But the point is that this Vij essentially goes as 1 over r to the power 6, which means that if you tune this V0 to be strong enough, you are going to achieve what is called a Reedburg blockade. That is, if you put in an excitation on any given atom, energetics is going to prevent excitation of the atom in the next site. Okay. So this Vij Nij essentially is a term which implements that. So if this Vij is something like some number V0 divided by I minus j to the power 6 modulus of that, which means that when I and j are nearest neighbor, if V0 is large, then this just imposes a constraint that you cannot have two Reedburg excitation on neighboring sites. But now you see that this, okay, and so let me just, now you see that this system is not too different from this dipole system that I talked about. Because if I do simply a mapping between this sigma z and the dipole density 2nl minus 1 and sigma xy with d plus d dagger, you see that this, in the spin language, essentially this Reedburg atom is same as the dipole model that I talked about. And here I would define a projection operator P, which is 1 if the spin is down and 0 if the spin is up. And if you put in this term, it just achieves the constraint that if you put in an upspin on a given site, then you cannot have upspin on the neighboring site. Okay, so that's one way to implement the constraint of the model. But let's just go back to experiments and see what they see. So if they increase this detuning, and we have the constraint that you cannot have two neighboring sites to have up, then increasing this detuning means that if your detuning is large and positive with a minus delta term, what you are going to see is that there would be maximum number of Reedburg excitation, which again is half the number of lattice sites. You can either have them at even or the odd this thing lattice sites, and that's the Z2 ordered state. But you can also go into states here where essentially you can have this Reedburg blockade for two consecutive sites, not one. So you make this V0 even larger, and that is achieved in experiments as well. So you can have Z3 orders and even Z4 ordered states. Okay. So this experiment not just implements the dipole model, it implements also states where the ground state is breaks Z3 and Z4 symmetries, and the critical phenomenon which takes between this at the critical point between this disordered and the Z3 ordered state belong to a 3-state Potts model kind of transition, and here it's a 4-state Potts, etc. So these are supposed to be non-izing critical points which are realized in this kind of non-interacting systems. Okay. So now people recently have looked into these phases of 2D Reedburg atom arrays. So what I have talked about till now is this one-dimensional chain of these Reedburg atoms, but now people have looked into the phases of this, And this is from Subir's group in Harvard. This is a theoretical calculation done by Ryan Samazdar and others. And apparently, so you essentially change this interaction radius. That's one of the axes, and this is the, so your Vij goes as V0 by R to the power 6. So you change R, which means you are changing the interaction strength, and here you are changing detuning as a function of detuning. So at large detuning, you see that there are many other possible ordered phases that comes in a square lattice, whereas Ashwin's group at Harvard looked into this on a Kagome lattice, okay, or rather I should say on the where the atoms are at the link of the Kagome lattice. It's not exactly a Kagome lattice, it's called a Ruby lattice, but nevertheless, I mean, and there, because this is a non-bipartite lattice, they find a region where they can find some spin liquid type of behavior of this using this Reedburg atoms, and this would be one possibility of realization of spin liquids using this Reedburg stuff. So this is where the focus is right now, this understanding phases of 2D Reedburg stuff. And also what I am not going to talk about, and I am almost done, so let me just take a minute to say, is that all of this system gives very interesting non-equilibrium phenomenon, including observation of something called quantum scars. And let me just show you one plot. So here what they do is that they go into some non-equilibrium configuration starting from this Z2 ordered state, and they look into how the density-density correlation, or some domain wall density which is equivalent to some density-density correlation, behaves as a function of time starting from that non-equilibrium state. And they see these long time oscillations, which is in complete violation of what you expect from theoretical results, where theoretical results tells you that you should go to a steady state and get a steady value very fast. This is a principle that goes by the name of ETH, or eigenstate thermalization hypothesis, which is violated here. And people tried to understand why, and when they tried to understand why, they found that these systems host a special set of many body state called quantum scars, which controls these dynamics. So I am not going to say much about this, but the interesting thing about this ultra cold atom system is that not only they emulate ground states of strongly correlated models, they also give us insight into quantum dynamics, out of equilibrium dynamics of strongly correlated models, which is completely impossible in standard laboratory settings, because you are not going to get a coherent quantum systems which is going to show you this dynamics. So let me now take, how much time do I have? 5 minutes maybe? Okay. So okay, I am going to finish. So in the last 2 or 3 slides, what I am going to talk about is a recent work of ours, and sorry for flashing that, but the point is that it's something that it's really surprised us. So let me just try to share that surprise with you. So we were looking into this Reedburg ladder with staggered detuning. What does this mean? So in the previously you saw that in this kind of setting, we were talking about this detuning, which was done, and typically when people look into this experiment, this detuning was said to be the same value for all atoms, because that's experimentally very easy. And I must say that this staggered detuning thing theoretically is very interesting, but people haven't really done experiments using this yet. Okay, so that disclaimer is there. But I'll tell you why this is interesting. So let's say you have this staggered detuning, so that on each side you have a uniform piece which is lambda, and you have a piece which is delta, which now varies between odd and even sides. So this basically means, what I am saying is that you take a bunch of atoms in an array and you just detune the odd ones in a particular way and the even ones in another particular way. Okay, so that gives you this. And now instead of a chain, I am going to take a ladder, and my and basically the rest of it is same as this Reedburg atoms. Okay, so there is a 1 over R6 potential and everything. But the constraint now, what this potential is going to implement, is that now you see, because of this ladder, if you put in an up spin on any one given site, that is a Reedburg excitation on any of this given site, then you are not going to have Reedburg excitation on the left and the right neighbors, but also on the immediate down point on the other chain. So the Reedburg excitation eliminates will be eliminated on 3 sites, which is immediate neighbors of this this up Reedburg stuff. So we write down a Hamiltonian based on this. So it has a sigma x tilde, which tells you that you can flip spins, but only putting in the constant, and then there is this staggered detuning part. Now, what does the ground state phase diagram look like? Well, that's not too difficult to understand. So just first just imagine that this W is 0, okay. So I am just going to deal with this on-site term. You see that when lambda is large and negative compared to, so delta is put to be 1 in all the calculations. So when lambda is large and negative, you don't want to flip up spins, okay. So all the spins should be down. So your total net excitation density of Reedburg would be close to 0. So that's the all down states on both the ladders. And when the lambda is large and positive out here, you want to flip as many Reedburg excitations as you want, which essentially means that you are going to excite, let's say, this and that, etc. And then on the next site, it would be something like, so you excite even sites on the first ladder and the odd sites on the first this thing. So you are going to have a total half of excitation density, half on each of the ladders. But there are 2 possibilities here, because you could choose the excitation sites to be even on the first lattice and odd on the second, and vice versa. Okay, so there are 2 degenerate states again. That's the Z2 symmetry broken state. But interestingly, what happens in between is the interesting thing. So when lambda is between -1 and +1, that is, so when lambda is, let's say, out here, you are going to see that because of this factor of -1 to the power j, it is favorable to put in a Reedburg excitation on an even site, but not on an odd site. Okay. So you see the even site costs an energy lambda plus delta, and if lambda is negative, that's small. Whereas on an odd side it costs lambda so on an odd side it calls lambda minus delta. So with this minus sign, if lambda is negative, then it's large. So 1 Reedburg excitation per 2 even sites on each chain. Okay, that's what you are going to create. Because if you create 1 excitation on one of these even site, you cannot create an excitation on the site immediately below. That's the constraint for you. So this means that there is a macroscopic ground state degeneracy, because if you have 12 sites on each chain, you are going to sort of have a 2 to the power L degeneracy. Okay. So this means that your classical ground state has a macroscopic degeneracy, which is going to be only lifted by order by disorder. Okay, quantum fluctuations, which should come from this W stuff. So look, this order by disorder mechanism giving rise to order in ground state, the quantum fluctuation giving rise to order in ground state is nothing new. So this has been known since 1980s, and people have looked into this both in context of thermal steady state as well as ground state of quantum systems. But here what is a bit interesting is that when we do this, what we find is that inside this plateau at around this lambda by delta equal to 0.33, we have a Ising-like transition, which is something that Madhumita, my student, found out numerically. And when she came up with this plot, I just drove her away from my office saying that this cannot be, so go away. But she was very persistent, and then we realized why this is happening. All credit goes to her, of course, for this numerics. The point is that it seems that there is a Ising transition right here, and apparently we could identify what the states are on both sides. Here on the site where lambda is on this side where lambda by delta is greater than 0.33, what we find is the following. You see that here there is a twofold degenerate ground state, and the Reedburg excitation occurs on only one of the ladders. So you could have all the excitation on the first ladder, that's one possible ground state, or all the excitation on the even sides of the second ladder, that's another possible ground state. That's the Z2 symmetry breaking. Whereas on this side there are many, it's a superposition of many Fock states, including states where there are excitations on both ladders. Okay. So this state is unique, it doesn't break any symmetry, whereas this state does, and therefore they are separated by a quantum phase transition. But now the question is, why does this happen? Now, to do this, what we did is to do an effective perturbation theory, which tells us that there are two processes which gives rise to this important contribution to this order by disorder mechanism. The first one is that you start from this ground state and you create an additional Reedburg excitation here, okay, on the square diagonal site out here, which of course is creating a Reedburg excitation on an odd site, and therefore it's a high energy state. But then in the next process you go back here. So this process can only happen if all the Reedburg excitations are on this site, okay, because if there is anything nearby here, you cannot create this excited state, and therefore this process prefers all the Reedburg excitation to be on one of the ladders. Whereas the other term that we have is a process like this. So you start from a ground state like this, and then what you do is that you eliminate a Reedburg excitation out here. You eliminate this Reedburg excitation at 2J1, but then recreate it at 2J2. Okay, so you just flip between rungs of the same site of the ladder. Okay. This essentially wants maximum superposition of states with Reedburg atoms on both ladders. Okay. So when this process wins, you get the state which is unique superposition of all this. But when this process wins, you get a state which has all the Reedburg excitation either on one ladder or the other. This means that these two terms are competing, and it's the competition between these two that gives rise to an Ising transition. And this is an example of a transition which is completely stabilized by a order by disorder mechanism. If you just looked at the Hamiltonian, you are not going to guess this transition. So of course there are many examples of phases in quantum theories which are stabilized by order by disorder, but this is an example of a quantum phase transition which is completely stabilized by order by disorder mechanism. And then we of course did some more realistic calculation, keeping in keeping in proper 1 over r to the power 6 interaction and all that. The transition survives, its position changes, but it does survive. And more interestingly, this gives rise to a class of spin models where instead of a 2-leg ladder, you can have a L0 leg ladder, and we check numerically that for a 3-leg ladder, this gives rise to a ports, 3-state ports, and so on. So this gives you a generic way of giving rise to a class of quantum phase transition which is completely stabilized by order by disorder. And this, I guess, is where I would like to conclude by saying that this interesting transition and phases can all be generated by cold atoms and lights and atomic physics in some sense. So I think I'm going to stop here, and thank you for your attention.
Questions?
I have, thanks for this very nice talk. I have two questions. One is in the previous talk when you showed that there is a way to generate electric field in this cold atom.
Sure.
So are there any non-equilibrium phenomena there, like
yes,
generation of birefringence or pair creation, Schwinger pair creation type of thing? Or the electric field is small enough?
No, so in some sense you see the point is that here the electric field is a large thing, because U and E are the large amplitude terms in your Hamiltonian, but U minus E could be small. So so of course those kind of things can happen, but not within the subspace that we are looking at. There the electric field is large, and any kind of dynamics that you are talking about, that's going to take you outside this subspace.
And in this staggered Reedburg case, you have this different possibilities of Z2 and Z3 Potts model.
That's right.
So if you have this effective Hamiltonian, is it possible to get an order parameter for this? Like you can
Yes.
see like a Polyakov loop
Yeah,
kind of.
so this is something that I haven't talked about, but let me just tell you that if you take, so if you now define a pseudo-spin operator, which is, do I have a chalk? Yeah. So if you define a pseudo-spin operator, S2j z, sorry, S2, okay, let me define a state which is 2j1 down 2j2. Okay, this means that it's on a 2jth site of the first ladder, up spin, and 2j2. And so let me call this as up. And then there is a down, okay, which is just this. Now, in terms of this up and down, I can define my spins, and it turns out that if I sort of take this and define a spin such that up is half into, this is the pseudo spin, this thing, then this whole thing becomes, in this language, so it's just Ising model, sorry, there is a factor of 2 here, that's all. So this is an Ising model in a transverse field, and the order parameter is just this S2z, okay. And it will also tell you by Kramer-Swannier duality, this thing, the transition is going to get at 2 alpha naught equal to 1, and if you put this 2 alpha naught equal to 1 out there, okay, so there is a definition of this alpha naught and all that, and you see that the position of the transition exactly matches with the exact numerics. So simple duality just works out here. So yes, there is a order parameter, and it's really the difference of up spins on the even sides of the first and the second ladder. So that's the.
Yeah, so I have a question from the first slide. You told like we can find a momentum to temperature relation. Is there any closed expression for that?
Sorry, let me get to that slide.
So in the slide 1 you told
Slide 1?
Yeah, yeah,
Okay.
from momentum to temperature, like that.
Here or?
For the momentum distribution.
Oh, this is just the width of the peak. So if you take a boson, a bunch of bosons, and you try to find out the density distribution of that at finite temperature, you are going to of course get in momentum space a peak, right? Because most of the bosons are at k equal to 0. The width of that peak, how much the bosons have moved up across, well, that depends on how interacting they are, and of course also on what the temperature is. You know, because interaction and temperature is what scatters the boson from k equal to 0 to finite momentum states. But here you can almost neglect the interaction, or at least they can put in some corrective factors due to interaction. But then it's just because of the temperature.
So is there any theoretical expression?
Yeah, it's in standard textbooks. I don't have it at the top of my head, but I mean, you can just. So for example, if you go to Carson Huang, they should have this expression.
Yeah, like for the energy to temperature is just like the expectation value compared with the classical thing like e to the power minus beta, I think. Yeah.
That too, and also there is this thing that, you know, if you take the momentum, just calculate the momentum distribution of a bunch of boson using Bose-Einstein statistics at finite temperature, you are going to get a distribution like this, and the width of this is something you can just read off from that distribution.
So I have
In terms of temperature, that is, yeah.
So I have another question. So as you mentioned about the scars in the 1D Reedburg atom.
Yeah.
So what I read, like only that special state don't thermalize, like Z2, Z3 states.
No, it depends actually. So when I was talking about scars, I had in mind this Z, what is called typically the Z2 scars. That is, scars which have large overlap with the Z2 state. And this is what the dynamics was saying. But there are also scars which has large overlap with Z3 state, and scars like that is possible. So what happens for the scar states is that these are bunch of special states which are almost in the middle of the spectrum. But as you know that if you have a finite Hilbert space, the states in the middle of the spectrum, those are the states with extensive energy density, right? I mean extensive energy and therefore finite energy density. And therefore concomitantly their half chain entanglement entropy is going to be obeying a volume law. Okay, so you take a state, you make a density matrix out of this, and then you integrate half of the chain of that density matrix and see what the entropy is. So that's going to scale as a volume law for this class of states, whereas for the ground state it scales as an area law. That's the normal thing that happens. Scars are states which are in the middle of the spectrum, but they have almost area law like behavior for this entanglement entropy. And that's what makes them special. They don't really mix with the thermal states with volume law entanglement which are near them, because they have very different structure, And so that's why they are special. And once you start a dynamics which has large overlap with the scar states, this dynamic stays within the scar states for a very long time, because they don't simply leak out, because of the low overlap between the scar states and the other system. And that's why you see oscillations, because these are scar states are fewer in number. It's a order L subspace instead of a order 2 to the power L total Hilbert space.
So is that any experimentally like speciality about those state in the 1D, so that in the future we can see like similarly in the 2D Kagome or in the Reedburg lattice?
In those lattices it's not known whether scars exist or not. Most of the examples that I have come across are for 1D lattices, and that too for bosonic or spin models. So one thing that we were discussing, Ajit and I mean having possibility of fermionic scars and that's an open question still. It's not clear whether they are stable. And the second thing is that examples of scars in higher dimension, that's also another open question. And this is more difficult because of the following reason. You see, the number of scar states is order L, whereas the Hilbert space dimension is 2 to the power L, or some number to the power L, right, exponential in L. In 1D you can still try to find this out. But as you go to higher dimension, this is like literally searching for a needle in a haystack, right, because it's order L square states at most in order 2 to the power, within order 2 to the power L square states. So unless you have some theoretical input, it's very hard to search numerically. So that is another reason why it hasn't been. So people have been looking into this kind of phenomenon in 2D and higher dimension, but it's not entirely clear what this is going to lead to. Not to me at least.
There's actually a question on YouTube. So it says that even for t equal to 0, we can have hopping whenever mu is integral multiple of u. So physically, what can be happening which is allowing this hopping possibility?
I'm sorry, could you repeat this? Sorry.
So let me repeat slowly. So even for small t equal to 0, we can have hopping whenever mu is integral multiple of u. So physically, what can be happening which is allowing this hopping possibility?
You are not really, okay, that's a tricky point. I mean, you are not really having hopping like that. What you are having is a situation where two states with boson number n and n plus 1 are exactly degenerate.
Yeah.
Okay, so the mod state is typically not there, because that's my way of understanding it, but maybe there is a better explanation actually.
Okay. So you want?
Yeah.
So I was thinking like when you have these, let's say a 2 atom per site Mott state, what happens if like one of them is an impurity, like which has different on-site interaction than?
Oh, but then you break translation symmetry at the Hamiltonian level, right?
Okay. Then
So that of course is going to have some rich physics.
okay.
But I haven't looked into this, and one of the reasons why people haven't looked into this so much is that experimentally it's a very hard thing to engineer. Because you see, in all of these optical lattices, the bottleneck is that you cannot really address single sites.
Yeah.
All you can address is the thing as a whole, and this is another reason why, for example, the staggered potentials, the staggered detunings in Reedburg atoms haven't been experimentally realized till date. Theoretically, these are very interesting systems. For example, as Sayantan knows very well, this is one of the systems where you can get quantum link models, which shows a property called confinement-deconfinement transition, which is very exciting because this is typically predicted in terms of in context of lattice QCDs and stuff like that. But this could be another platform, a different platform. But the experimental bottleneck is this to achieve staggering. So that's not done yet, and the reason is that the single site thing is very hard to implement.
So could there be an effective model like where you put some percentage of impurity and then like it has some average effect on the whole system?
In principle, yes, sure. It could have some average effect on your system, but then you break translational symmetry at the level of Hamiltonian, which is different from here where we are breaking translational symmetry at the level of states in some sense.
Are there any other questions? Okay, so if there's no other question, I'll just ask one final one.
Sure,
So in this Reedburg chain, if you allow for diagonal hopping in the ladder,
More interesting stuff.
would it survive or?
No, that immediately gives rise to a frustration of some
That's
sort.
what I was thinking. So probably
Sure.
it goes away.
Not chain, but you are saying 2D Reedburg
Yeah, the 2D Reedburg
square
array.
array, right? Yeah, that's another thing. But you see, again, typically, what happens is that in a realistic system, first of all, Reedburg atoms don't hop. Okay, so you have to get some way of engineering that kind of thing.
Yeah.
In the tilted stuff, you can, but that what it is going to do is to create longer length dipoles. Okay, and that could in principle be possible, but that's a separate system. I think some people did study it, I didn't, but yeah.
Okay, so since there are no more questions, let's thank Krishnendu once again for